Imagine for a moment that everything you know, every galaxy, every star, every exoplanet, enthusiastically swirling around its sun like a cosmic ballroom dancer, is tucked inside something that behaves suspiciously like a giant celestial drainpipe. Not a graceful marble fountain, no. More like the universe's plumbing system, except the pipes are made of space-time, and the water pressure is replaced by gravity so strong it could wrestle a mountain into dust. This is the kind of picture that immediately grabs the imagination. The idea that we might be living not in a universe that began quietly with a big, bright bang, but inside the hidden interior of a black hole. It sounds like the sort of theory you come up with at 3 in the morning when the universe feels a little too big and your snack choices feel a little too questionable. Yet somehow this theory refuses to slink away into the shadows. Instead, it sticks around, waving its cosmic arms and shouting, "Look at me! I might actually make sense." Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. There is something undeniably magnetic about black holes. Even before we understand the physics, the name alone sounds like the universe's version of a mystery novel, a place where light disappears, time gets weird, and the usual rules step outside for a smoke break. The idea that such a thing could lead not to destruction but to creation hits that perfect sweet spot between logically intriguing and delightfully absurd. It is the astrophysical equivalent of hearing that your grumpy old washing machine contains a portal to a tropical resort. You know it should not be possible, but you desperately want to peek inside just in case. Part of what makes this idea so irresistible is that black holes already demand we think beyond our usual intuition. Most celestial objects behave politely, maintaining predictable orbits and emitting radiation like dependable cosmic lighthouses. Black holes do none of that. They sit in space like dark, silent pranksters, bending everything near them, light, matter, time itself, into shapes that would make a contortionist jealous. When an object crosses their boundary, the event horizon, it does not come back out, at least not in any form you could recognize. So naturally, scientists wondered whether all that matter and energy is really vanishing or just slipping into someplace else. Maybe on the other side is a new region of space-time, a secret backstage area of the cosmos where new universes could bloom. Suddenly the black hole stops being a tombstone and starts looking suspiciously like an egg. This brings us to the truly fun part, wondering whether our own universe might have begun this way. Picture the earliest moment of existence not as a bang, but as the instant someone else's star collapsed under its own weight, forming a black hole so intense it cracked open a new realm, ours. Cosmic hand-me-downs, but elegant. It is a theory that lets us imagine the cosmos as an endless lineage of universes, each one tucked inside the black holes of its parent universe, a kind of cosmic Russian nesting doll, except instead of painted wooden faces, you get swirling galaxies, and the occasional rogue asteroid that behaves like an overly energetic puppy. Even if this idea sounds wild, it refuses to die because it taps into something deeply human, the urge to look behind the curtain. We do not just want to know what the universe is. We want to know where it came from, what came before it, and whether there is a larger context in which all this cosmic theater takes place. And the black hole universe theory gives us a tantalizing narrative. It says, yes, there may be more. Yes, your universe might not be the main stage, but just one scene in an ever-expanding cosmic play. There is humility baked into it, and a sense of possibility that feels almost mischievous. It also helps that black holes are famous for breaking all the boring rules. They are like the universe's rebellious teenagers, insisting that physics should chill out and try something weird for once. They warp space, they stretch time, and they refuse to let anything escape. So if any object were going to pull an unexpected trick like spawning an entire new universe inside itself, a black hole is the obvious candidate. Stars certainly are not doing this. Nebulae look gorgeous, sure, but they are just big clouds with artistic ambitions. Black holes, though, they have that chaotic energy that makes you think they might be up to something. And so the theory stays alive, not because we know it is true, but because it refuses to be ignored. It winks at us from the edges of physics, saying, if you think the universe is strange now, just wait until you see what might be hiding in the dark. It is a theory that stretches curiosity the way a black hole stretches light, pulling us deeper toward its center, not to crush us, but to feed that eternal human hunger for answers wrapped in mystery. Long before black holes became pop culture icons with the charisma of cosmic celebrities, they started as strange mathematical creatures. No telescopes, no dramatic space-time animations, just equations that refuse to behave politely. When early theorists first stumbled upon the idea, it was like discovering a locked door in the attic of physics. No one knew who put it there or why it was locked, but it absolutely demanded investigation. What made that locked door especially enticing was that every time someone checked the math, it whispered the same thing: open me if you dare. And physicists, being the curious troublemakers they are, dared. It began with the exploration of gravity taken to its extreme. Researchers were trying to understand what would happen if an object became so dense that its gravitational pull turned from strong to absurd. The early equations suggested that space-time would not simply curve gently, the way the surface of a trampoline dips beneath a bowling ball. Instead, the fabric would plunge downward, forming a kind of funnel so deep it effectively left the universe as we know it. This set off a quiet alarm in the minds of theoretical physicists. Gravity had always been the dependable force, the one that politely kept planets in place. But here it was threatening to tear a hole straight through the cosmic tablecloth. That made everyone uneasy in the best possible scientific way. As more scientists probed this mathematical abyss, they noticed something even stranger. The interior of this gravitational funnel behaved as though it had regions, zones, shapes, and boundaries that were not part of the familiar universe. The equations seem to be describing pockets of spacetime that existed beyond the reach of ordinary physics. These were not simple cavities or caves. They looked like entirely new environments with their own rules, as if the universe had hidden bonus levels waiting to be unlocked. Naturally, theorists began asking the question that would lead to decades of fascination. Could these regions be internal worlds? It was an idea no one wanted to claim at first, because it sounded dangerously close to fantasy. Suggesting that black holes might contain internal cosmic spaces felt like proposing that your vacuum cleaner secretly harbors a tropical island. Yet the math kept pushing the discussion back to that possibility. The deeper the equations were explored, the more they suggested that inside a black hole, space-time may not simply collapse into nothingness. It might rearrange itself into a new configuration, perhaps even expanding in ways our outer universe could not witness. This subtle mathematical hint grew louder over the years, like background music, slowly turning into a full orchestra, insisting on a dramatic reveal. As time went on, different scientists returned to this curiosity with fresh eyes. Every decade or so, a new wave of thinkers revisited the problem and discovered that the idea still clung stubbornly to the edges of physics. This persistence became something of an intellectual mystery. Usually, speculative ideas fade when the math tells them to sit down. But this one refused to sit. Instead, it stood tall, waving its hand like a student desperate to participate. Even the most rigid theoretical frameworks kept circling back to the notion that a black hole might not be a simple endpoint, but instead a doorway into a deeply complex internal geometry. Part of what fueled this recurring fascination was the compelling combination of danger and potential. Black holes were already remarkable for stretching natural laws to their limits. They crushed matter, squeezed light, and tangled time into knots. So the idea that they could also contain vast new landscapes of space-time felt oddly fitting. If you were looking for a place in the cosmos where something unexpected might occur, a black hole was the universe's way of saying, "Try here. Odds are good." Curiosity also deepened as general relativity matured. With every new solution discovered within the equations, physicists found themselves confronted by bizarre interior structures, tunnels, extended regions, and mathematical expansions that had no direct analog in everyday experience. These structures were not metaphors or imaginative sketches. They were rigid mathematical outcomes. And if mathematics is the universe's handwriting, then its message was uncomfortably clear. Black holes might be much more elaborate on the inside than anyone had predicted. This idea kept resurfacing because every attempt to simplify black holes brought the mystery back like a cosmic boomerang. Remove assumptions, add assumptions, tweak the parameters. No matter what theorists tried, the interior refused to collapse into a clean, tidy endpoint. Instead, it remained a labyrinth that demanded interpretation. Were these internal structures physical? Were they a sign of new physics that had not yet been discovered? Or were they hints that our understanding of space-time needed a serious renovation? Each question led to new investigations, and each round of investigations coaxed the same whisper from the equations. There is more in here than you think. The repeated return to this idea is a testament not only to black holes' mathematical stubbornness, but to the enduring human desire to push boundaries. Scientists could not bear the thought that the universe might contain vast interiors hidden behind horizons, quietly existing without our knowledge. That possibility was irresistible. It made everyone feel like cosmic archaeologists brushing dust from the entrance of a sealed ancient chamber. If there was even the slightest chance the chamber contained something extraordinary, it had to be explored. So the idea persisted, not as a bold claim, but as a glimmer that refused to fade. It lived in equations, in discussions, in debates over chalkboards filled with scribbles that looked like the universe trying to express itself in secret code. And eventually, all those whispers in the math built up into a theory that modern thinkers still chase today. The possibility that black holes do not merely swallow worlds, but might harbor worlds of their own. A black hole is one of those cosmic ideas that sounds simple at first, like the universe is offering you a neat little package, a place where gravity is so strong that nothing can escape. But the moment you look closer, it immediately reveals itself to be as straightforward as assembling furniture without instructions while blindfolded. To really understand what a black hole is, you have to step away from the usual picture of space as a giant empty room, and instead imagine space-time as something flexible, almost like a stretchy sheet of dough, except this dough is not delicious, and it absolutely will not rise politely in the oven. It curves, it bends, it dents, it twists. In fact, it behaves like cosmic taffy being kneaded by forces far beyond anything we experience on Earth. Normally, when something with mass sits in space-time, like a planet, a star, or a very confused comet, it makes a gentle dip in that taffy. A star might make a deeper dip, but everything stays friendly. Space curves softly, gravity behaves predictably, and the universe quietly minds its own business. But when a massive star collapses under its own weight, all that mass gets squeezed into a dramatically tiny space, like someone trying to compress an entire library into a single grain of rice. Suddenly, the dip in space-time stops being a dip. It becomes a plunge, a drop. A bottomless well that looks like the universe took one step too far and fell through the floor. That plunge is what we call a black hole. It is not really a hole in the everyday sense. There is no tunnel, no cave, no swirling drain with a neon sign that says danger. Instead, it is a region where gravity has gone so far off the deep end that the usual rules politely bow out. Inside this region, space-time curves so violently that everything, even light, the universe's fastest and most stubborn traveler, becomes trapped. It is as if gravity turns into a cosmic bouncer, crossing its arms and saying, "Sorry, nobody gets out." The edge of this region is called the event horizon, but you can think of it as the point of no return. Imagine walking toward the edge of a waterfall without realizing it. Upstream, everything looks normal. The river seems calm. Then you cross a line where, no matter how strong a swimmer you are, the current drags you forward. That line is the event horizon. Except in the case of a black hole, the current is gravity, and instead of water pulling you downward, space-time itself is funneling you inward with a determination that borders on rude. But what makes this gravity so intense? It is not that black holes are greedy. They do not go around vacuuming up everything in sight, despite their reputation. Their gravity only feels extreme when you get extremely close. What makes them special is the absurd concentration of mass. The more mass you cram into a tiny region, the more space-time distorts around it. And a collapsed star that becomes a black hole compacts its mass so tightly that the curvature of space-time becomes steep in the same way a cliff is steeper than a hill. You could walk on the hill. You could not casually step off the cliff unless you enjoy regretting your choices. To picture the stretching of space-time near a black hole, imagine pulling a piece of taffy so hard that one end thins out like a strand of silk, while the other stays thick. The stretched part becomes elongated, thinner, more distorted. Near a black hole, this stretching becomes extreme in all directions. If you were somehow falling toward one, and please do not try this at home, you would be tugged so much more strongly in the direction of the center than in the sideways directions that your body would start to stretch. This process has a name, but in plain language it means you would become spaghetti. The universe does not care how dignified you feel. It will turn you into cosmic pasta if you get too close. From the outside, though, a black hole looks surprisingly calm. It does not glow or shimmer or announce itself. It is simply dark, a region where light stops communicating forever. You would not see the interior because any information inside cannot leave. It is like trying to watch a movie, but the screen has been unplugged and dropped into a bottomless pit. All you can see is the aftermath, the swirl of gas, the distorted starlight, the strange gravitational dance of objects orbiting too close. What makes black holes especially enchanting is that they are not supernatural. They are not cosmic monsters. They are simply the result of physics pushed to its limits, like a recipe taken far beyond the recommended temperature. They show us that gravity is not just a gentle force keeping your feet on the ground. It is capable of reshaping the universe itself when given extreme conditions. A black hole is what happens when nature decides to crank gravity up past any setting you would expect and refuses to apologize for the consequences. Yet for all their intensity, black holes are also strangely elegant. They take something as simple as mass and turn it into an object where time slows, space curves, and the universe quietly whispers, "You are now entering the deep end." They remind us that space-time is not a static backdrop. It is a living, flexible, dynamic fabric, one that can be stretched, bent, twisted, and plunged into depths so profound that even light must surrender. And in that surrender, the universe reveals one of its most dramatic masterpieces, a place where the rules we know are not broken, just taken to such extremes that they look like entirely new rules. A black hole is nature's way of showing off, sculpting a region where gravity speaks with its loudest voice and everything else falls silent. The event horizon of a black hole is one of those cosmic landmarks that manages to be both completely invisible and absolutely unmistakable, at least in concept. It is the universe's most intense, authorized personnel-only sign, except instead of a rope and a grumpy attendant, the boundary is stitched directly into space-time, and the penalty for crossing it is that you will never return, send messages, or even wave dramatically on your way out. It is the point where the gravitational pull becomes so overpowering that even light, the universe's speed champion, gives up and mutters something like, "Nope, that is too much commitment," before vanishing forever. Yet if you were drifting toward it, you would not see a door, a shimmer, or a swirling cosmic force field. Instead, you would drift across it with the same quiet nonchalance as stepping over a line painted on a sidewalk, completely unaware that your exit strategy has just been permanently deleted. The event horizon works a lot like an invisible trapdoor. On one side, the universe plays by the usual rules. Clocks tick forward, directions make sense, and movement feels like movement. On the other side, everything shifts into a regime where the rules warp in ways your senses cannot interpret. If space were a map, the event horizon is where the map stops being a guide and starts behaving like a prank, rearranging roads and leaving you wondering whether down is still the same direction it used to be. Before crossing, everything seems deceptively normal. You would see stars, distant galaxies, maybe the glow of gas swirling around the black hole. But as you drift closer, the behavior of light around you becomes stranger. Light that tries to escape the black hole's pull curves sharply, looping and spiraling in weird arcs that would give even the most resilient navigator an existential crisis. The closer you get, the harder it becomes to figure out where anything is. Directions that used to be trustworthy, up, down, sideways, forward, start feeling like they are taking advice from a funhouse mirror. And then, without fanfare, you cross the horizon. No sound, no flash, nothing telling you that you have passed the point of no return. Your spaceship's instruments would still blink cheerfully, blissfully unaware that every message they send is now trapped. You would still see the universe, but it would appear frozen in a strangely distorted way, as if someone paused the cosmic movie. Time, from your perspective, would feel normal enough to lull you into complacency. But the universe outside would see something very different. To outside observers, it would look like you were gradually slowing down, your movements stretching into slower and slower motion until you appeared stuck, frozen just above the event horizon and fading into darkness. They would never witness you cross it. To them, you are eternally approaching and never arriving. Like a cosmic version of trying to get your phone to load a web page on painfully slow internet. Inside the event horizon, direction becomes a slippery concept. In the outer universe, we think of time as something that flows forward, and space as something we can move through freely. But once you have crossed that invisible boundary, the mathematics of space-time rearrange themselves. Time is no longer something you can choose to move through. It becomes more like a gravitational slope pulling you inward. Every path, every trajectory, every possible decision funnels toward a single inevitable destination. It is not that you are being pulled in a direction you do not want to go. It is that direction itself becomes a very limited menu, and all the options lead toward the center. Your sense of place, that basic human feeling that tells you you are here rather than there, begins to unravel. Inside the horizon, the flow of space-time does not guide you the way it does outside. Movement becomes complicated because the geometry of space no longer behaves in familiar ways. It is like stepping into a room where gravity pulls sideways, the floor tilts upward, and the ceiling decides it wants a promotion and becomes the new floor. This is why crossing the event horizon is like pressing a cosmic delete button on your internal GPS. Not only does the universe refuse to tell you where you are, it actively stops having a clear answer itself. Yet from your own point of view, nothing magical has happened. Your body does not suddenly stretch. Your ship does not spin wildly. You do not feel the boundary. The event horizon is, in many ways, a silent trickster. It looks harmless while hiding the fact that every possible future you have now funnels into the black hole's core. You are not falling in the way you fall on Earth. You are being carried by space-time itself, swept along like a leaf stuck in a powerful current. You have no way to paddle against it, no way to signal out, no way to escape. Even light, your usual faithful companion, cannot climb out to tell the universe where you went. The truly eerie part is how gentle everything seems during the transition. From your perspective, nothing dramatic happens at all. No alarms, no danger signs, no voiceover saying, "Brace for gravitational chaos." Black holes have a talent for hiding their most extreme physics behind a curtain of normalcy. It is only once you have crossed the event horizon that the hidden structure of space-time begins to reveal just how different the interior is from everything you have ever known. In a sense, crossing the event horizon is not about disappearing from the universe. It is about relocating to a region where the usual concepts of here and there lose their meaning. It is the universe's ultimate one-way door, quiet, subtle, absolutely unbreakable, and deeply uninterested in your escape plan. Outside, your story looks like it has paused forever. Inside, it continues on a path that only leads deeper, farther from the world you left behind, and firmly into the heart of gravity's most mysterious creation. To appreciate why black holes might create new internal regions, places so strange they behave like miniature universes, you first have to understand that space-time is not the stiff, inert backdrop we sometimes imagine. It is not a cosmic stage built from steel beams and unchanging flooring. Instead, space-time is a flexible, dynamic fabric, sensitive to every mass and every motion, almost like a living material that reacts to whatever sits on it. Think of it as a stretchy sheet of cosmic cloth. Set a marble on the sheet, and it makes a small dip. Set a bowling ball there, and suddenly the dip becomes a bowl. But set something much heavier, say, a collapsed star weighed down by its own gravitational intensity, and the fabric stretches so dramatically that the bowl stops being a bowl and starts turning into a deep funnel. And that funnel, if pushed far enough, might not simply continue downward. It might twist, pinch, or fold space-time into shapes that defy normal intuition. Space-time curvature is the heart of this transformation. Gravity is not a force pulling objects from a distance like an invisible hand yanking on strings. It is the bending of space-time itself. When a massive object sits in space-time, it alters the geometry around it. A planet orbits a star not because some mysterious force beckons it inward, but because the curved space-time around the star guides the planet's motion. The planet is simply following the most natural path, what mathematicians call a geodesic, like a marble rolling around the slope of a curved surface. This subtle insight, introduced through the equations of general relativity, changed everything. It meant the universe was not a static frame, but a malleable fabric, capable of being reshaped by mass, energy, and even pressure. Under ordinary conditions, this curvature is gentle. A star bends space-time smoothly, forming a graceful valley. But when a massive star undergoes gravitational collapse and shrinks far beyond what physics normally tolerates, space-time reacts dramatically. The curvature becomes steep, so steep that it no longer resembles a valley, but more of a plunge that seems to defy common sense. This is where the concept of a pinch or fold comes into play. When the collapse intensifies to the point that gravity overwhelms all other forces, the structure of space-time stops following the familiar dip model and may begin creating entirely new shapes within itself. Imagine pushing your finger into a piece of elastic fabric. At first, the fabric stretches downward. Push harder, and it stretches more. Push so far that your finger pierces through the fabric, and suddenly you have created a new connection, a new layer, maybe even a pocket or bubble beneath the original sheet. In this sense, extreme gravity might push space-time past its normal threshold, causing it to form regions that are technically inside the black hole, but not part of our observable universe. These regions could expand inward, forming their own interior geometries, completely cut off from the external cosmos. This is where the idea of mini-universes emerges. When space-time is pinched or folded under extreme gravitational stress, some theoretical solutions to Einstein's equations suggest that these internal pockets do not simply collapse into a point. Instead, they can open up into new domains, regions where space can expand, stretch, and behave independently from the parent universe's space-time. These regions are not just empty chambers. They can have their own time flow, their own curvature, even their own effective rules governing their internal evolution. If our universe were a gigantic cosmic book filled with stars and galaxies as its characters, these interior pockets would be like chapters hidden between the lines, unreadable from the outside, but vast and richly structured within. One of the most intriguing aspects of these internal regions is that they might grow. Once space-time pinches into a new domain, the pressures and energies inside could cause it to expand, not outward into our universe, but inward into itself. It would be like discovering a hidden room inside a house, only to watch that room rapidly enlarge into a mansion, completely invisible to the occupants outside. This internal expansion is not just a thought experiment. It is a genuine possibility that arises from certain cosmological solutions that allow regions of space-time to balloon independently once they detach from the external geometry. The notion that black holes could host such inward-growing regions challenges the popular image of a black hole as a purely destructive object. Instead of acting like cosmic shredders, tearing everything into meaninglessness, they might be cosmic architects constructing internal landscapes so elaborate they rival entire universes. And crucially, these inner regions would be inaccessible from the outside. The event horizon acts like a sealing boundary, trapping the newly formed domain and allowing it to flourish in isolation. But here is the real mind-bender. The internal region is not tiny in any meaningful sense. It might start small, but because space inside it can expand, that region could become unimaginably vast, while still remaining hidden behind the event horizon's boundary. From the outside, the black hole might appear relatively modest in size, perhaps spanning only a few kilometers across. But on the inside, the internal space could stretch into distances larger than our entire visible universe, like the cosmic equivalent of finding a castle inside a closet. This is the magic of space-time curvature pushed to its extremes, the ability to fold, pinch, and reshape reality into forms that defy ordinary expectations. When gravity pushes hard enough, space-time does not simply break, it transforms. And in those transformations, the possibility arises that black holes are not final destinations, but the beginning of entirely new cosmological realms, mini-universes thriving in the depths, sealed away but profoundly real. The word singularity has a dramatic flair to it, and for good reason. It conjures images of something ultimate, a point where physics throws up its hands and says, "I am going on break, do not call me." Traditionally, a singularity is described as a place where density becomes infinite. Space-time curvature shoots off the charts, and the known laws of nature stop being helpful. But infinity, as appealing as it is to mathematicians and people trying to sound mysterious, is often nature's way of telling us we have misunderstood something. When the universe gives you infinities, it is usually nudging you toward a bigger idea hiding behind the math. And in the case of black holes, that bigger idea is that singularities might not be points at all, but rather openings, gateways to new, expanding regions of space-time. The classic picture of a black hole places the singularity at the center like some terrible destination. Fall in, get crushed into nothing, end of story. But modern theoretical work increasingly suggests that this grim scenario might be far too simplistic. Nature rarely invests so much effort into sculpting something as dramatic as a black hole, only to end it with a simple, "You have reached the end of the road" sign. Instead, the singularity might be less like a destination and more like a passage, a region where space-time is rearranged rather than destroyed. To grasp this, imagine space-time not as a flat sheet, but as a multi-layered fabric. When gravity becomes extreme, really extreme, the kind of extreme that makes regular stars faint from exhaustion, this fabric does not merely tear, it can fold or reconnect in new ways. The so-called singularity might actually be the point where this reconnection happens, a place where the old geometry gives way to a fresh piece of space-time with its own shape, its own direction, and its own potential to grow. In this view, what we have been calling a singularity is less a dead end and more a doorway covered in warning signs that say, "Not accessible from this side." This reinterpretation opens an astonishing possibility, the birth of a new expanding universe on the far side. If the collapse of a massive star leads to a region where space-time pinches and then inflates, that inflation could produce a universe-sized bubble, one that swiftly grows, smooths itself out, and evolves independently. It would not expand into our universe. It would expand into itself, sealed off by the event horizon of the parent black hole. From the outside, nothing special appears to happen. The black hole simply gains a bit more mass. But from the inside, an entire cosmos could be unfolding, complete with its own galaxies, stars, and perhaps some bewildered beings wondering where everything came from. If that sounds familiar, it should. Our own universe began with a moment of explosive expansion. We give it a name, the Big Bang, and describe it as the instant space-time leapt into existence. But nothing in our laws of physics forbids this expansion from being the interior of a larger structure. If the singularity inside a black hole can act like a seed that blooms into a new region of space-time, then our universe might not be an isolated miracle. It might simply be the inside of a black hole that formed in another universe long before we ever existed. Picture it. Somewhere in a grander cosmos, a colossal star collapsed, its core squeezing tighter and tighter, its space-time folding inward until, pop, a new expanding region appeared on the other side. That region, sealed off from its origin, bloomed into everything we know. Galaxies spun into existence, stars ignited, planets formed, drifted, collided, and reassembled. Eventually, one of those planets developed life that evolved the incredible ability to question its own origins. This entire chain of events might be the internal story of a black hole from an older cosmic realm that will forever remain invisible to us. This concept reframes the singularity not as an infinitely small point, but as a kind of cosmic seed. It contains the information and conditions needed to start a new space-time branch. But once that branch expands, it becomes a vast, sprawling universe in its own right. The connection to the parent universe is severed by the horizon, a kind of cosmic umbilical cord that does not allow two-way travel or communication. Each universe grows independently, oblivious to the one that created it. Of course, this raises the question of what the singularity looks like from the inside. Surprisingly, the answer might be nothing special. Inside the new expanding region, the violent collapse that formed the singularity is smoothed over by rapid expansion. the newborn universe would begin with hot, dense conditions, but that density would not be infinite. It would simply be high enough to begin the cosmic evolution we see etched into the background radiation today. Observers inside would not see a singular point. They would see the earliest moments of expansion, and then the vastness that grows from it. Thinking of singularities as gateways also sheds light on why the mathematics describing them often break down. The infinities that appear in our equations may not represent actual physical infinities. They may simply mean that the coordinate system we use, a coordinate system built for our universe, cannot follow space-time through the transition into a new region. It is like trying to describe a sphere using only flat maps. At some point, the map stops working, but the sphere does not stop existing. This reinterpretation is thrilling because it turns black holes into cosmic engines, not destroyers. They become part of a generational lineage of universes. One universe produces black holes. Those black holes produce new universes. Each universe might carry subtle fingerprints of its parent's physics, and the singularity, far from being a terrifying point of infinite doom, becomes the doorway through which entire new realities are born. If this is true, we are not merely living in a universe. We are living in a cosmic descendant, a space-time child, formed from the collapse of something grand and ancient beyond our horizon, a universe whose existence we can only imagine, but whose legacy may be written into every atom we are made of. The Big Bang is usually described as the universe's grand premiere, the moment everything burst into existence with all the subtlety of a firework going off in a broom closet. It is the defining beginning, the cosmic opening act, the second the clock of reality started ticking. But what if this explosive beginning was not the absolute start of everything, but more like a handoff? A relay baton passed from an older universe to ours through a black hole that collapsed in that older cosmic landscape. Instead of imagining the Big Bang as a lone miracle floating in the void, imagine it as the inside view of something collapsing elsewhere. A moment of birth triggered by a death that occurred far beyond our cosmic horizon. To explore this idea, picture a massive star in some parent universe undergoing gravitational collapse. It shrinks under its own weight, squeezing matter and energy into an unimaginably small region. From the outside, observers see the formation of a black hole, complete with an event horizon that locks away everything inside. But on the inside, a very different story might unfold. Instead of crushing matter into an impossible singularity, the extreme compression could trigger rapid expansion in an internal space-time pocket, a region not visible from the parent universe. That pocket, in its infancy, would experience a sudden surge of growth. To anyone inside it, the first moments of that expansion would look exactly like what we call the Big Bang. This perspective changes the flavor of the Big Bang dramatically. Instead of appearing from nothing, our universe would have emerged from a physical process, one linked to the natural life cycle of a star in another cosmos. It would make our universe not a lone miracle, but a cosmic heir, inheriting existence from a previous generation. And the moment of that inheritance, the instant compression snapped into expansion, would be the Big Bang itself. This reinterpretation helps resolve one of the strangest features of the Big Bang, how it managed to expand with such uniformity. The early universe was astonishingly smooth, almost eerily so, with temperature differences so tiny they make unremarkable seem like an understatement. Standard explanations rely on rapid early expansion to smooth out these irregularities, but the origin of that rapid expansion still feels like a riddle tucked inside a puzzle wrapped in a mystery. But if the Big Bang were the internal bloom of a black hole, the initial conditions might make much more sense. The collapse of a star in a parent universe would have squeezed matter and energy into an incredibly dense state, dense enough that when they bounced into expansion inside a new space-time pocket, everything would start off smoothed by this compression. It is like packing a suitcase so tightly that when the suitcase bursts open, all the clothes fling themselves outward in a beautifully even arrangement. A black hole interior would act as the ultimate cosmic compression chamber, setting the stage for the uniform expansion we see reflected in the earliest light of our universe. The birth of the universe inside a black hole also offers a wonderfully intuitive way to think about why the Big Bang happened everywhere at once. From the outside, the collapsing star in the parent universe shrinks toward its center. But on the inside, the new space-time region does not expand from a single point. It expands from every point simultaneously, because the interior region is the whole space. Just as the surface of a balloon expands everywhere as the balloon inflates, so too would a new universe blossom in all directions, making the idea of a central explosion irrelevant. There would be no center because expansion defines the entire domain. This framework also raises an intriguing idea about the Bang in Big Bang. Perhaps it was not an explosion in the traditional sense. Instead, it may have been the moment internal space-time decoupled from the collapsing parent structure. As the black hole in the parent universe formed, its interior geometry might have branched off and inflated rapidly, becoming causally disconnected from the world outside. To observers inside, that inflation would appear as a sudden explosive expansion, the closest thing physical reality has to a magical transformation. Another fascinating implication is that our universe's time might have begun when the interior of that black hole branched off. Time inside the expanding pocket would not have a meaningful link to the time of the parent universe. It would be as if a new timeline were printed in fresh ink, while the old timeline continued running on its own track. The Big Bang, in this sense, becomes the start only from our point of view. It is the moment our local space-time started ticking, even though something older may have set the whole thing in motion. Picture the parent universe as a vast cosmic forest. Every so often, a massive star collapses into a black hole. Each collapse plants a potential new seed, a space-time sapling, growing into its own universe in a realm invisible from the forest floor. If so, our universe is simply one of these saplings, grown large enough today that we see galaxies and clusters and filaments stretching everywhere we look. But the roots, the origin, the moment it all began, Those could lie in the collapse of a star we will never see, in a cosmos we can never reach. What emerges from this idea is a beautifully interconnected cosmic cycle. The Big Bang is not a solitary beginning. It is the internal ignition of a black hole that bloomed unbelievably into the sprawling cosmos we inhabit. Instead of a single universe that simply happened into existence, we become part of a lineage, a genealogical tree of universes sprouting from the gravitational collapses of countless cosmic generations. In that picture, the Big Bang is not the universe's birth cry, but its first breath after crossing the threshold from one reality into another. Cosmic background radiation is the universe's equivalent of morning fog, a faint, uniform wash of microwaves filling every corner of the sky, humming softly with information about a time long before the first stars blinked awake. It is an afterglow so ancient that it comes from an era when matter was still figuring out how to stop behaving like a temperamental soup and start becoming things like atoms, galaxies, and planets with strong opinions about gravity. Most people hear about this radiation as proof of the Big Bang, but if you examine it closely, it becomes far more than a simple leftover glow. It might be a subtle, stubborn fingerprint hinting at where the universe came from, possibly hinting at an origin tucked inside something else's gravitational collapse. What makes this ancient radiation so fascinating is how spectacularly uneventful it looks. Spread evenly across the sky, it arrives with almost the same temperature no matter where you look, as if the universe decided to paint everything in a very consistent shade of microwave beige. Tiny variations do exist, minuscule temperature ripples no larger than a few parts in 100,000. These ripples are not random static. They are fossils of early fluctuations, the slight clumping and stretching of matter that would eventually grow into galaxies, clusters, and entire cosmic structures. But beyond these small bumps, the overwhelming smoothness of the radiation raises a question that feels a bit like a cosmic eyebrow lift. Why is it so uniform? In a universe born inside a black hole, that smoothness would not be surprising. Before this new interior region ever began expanding, its contents would have been compressed by the collapse on the other side of the event horizon. That compression would have ironed out local differences, leaving everything nearly uniform before the internal realm even got a chance to stretch. When the expansion began inside, the microwave background that eventually formed would naturally carry that evenness. The radiation's uncanny smoothness might therefore echo the conditions imposed by the gravitational squeeze of a parent universe, a trace not of a single explosive moment, but of an intense compression stage that came before any expansion happened inside. Then there is the curious fact that the cosmic background radiation preserves a specific pattern, a faint code of temperature variations that look like a series of ripples on a cosmic pond. These ripples have sizes and amplitudes that match what you would expect from a region rapidly stretched to vast proportions. But the details of the pattern hint at something more. They show a striking coherence, as if the early universe's fluctuations were not only smoothed, but synchronized, like the universe began with its energy distribution already remarkably balanced, almost pre-tuned. That synchronized quality is perplexing if the universe began in complete isolation. But if it was born from the intense pressure of collapse in a parent universe, that balanced starting point feels less like a mystery and more like a natural consequence of being pushed through an environment where every particle was denied the luxury of keeping its own personal space. Another subtle clue lies in the energy scale of the cosmic background radiation. Its temperature today is just a few degrees above absolute zero. But tracing it backward through time reveals an early state of intense heat, hot enough to glow uniformly, but not so wildly chaotic that it would leave giant scars of asymmetry. The energy profile is calm, almost disciplined. If the early universe had originated from a truly uncontrolled explosion, you might expect more dramatic variations. But if the universe emerged inside a region that had been shaped by an external gravitational collapse, its initial energy budget might have been constrained. The radiation we detect today may carry the imprint of those boundary conditions, like fingerprints pressed into clay before the clay ever had the chance to harden. Some theorists have even pointed out that the large-scale uniformity of the cosmic background radiation might hint at an early causal connection, a state where everything could influence everything else before expansion carried regions apart. But such a connected state is puzzling if space-time sprang into existence with no prior structure. Inside a black hole, however, that connected state becomes almost unavoidable. Before the interior region expands, everything inside is packed so tightly that information has nowhere to hide. The cosmic background radiation's uniformity could be a whisper from that earlier stage, telling us that the universe began in a place where distances were compressed to meaninglessness. Another intriguing puzzle comes from the radiation's angular spectrum, the way the temperature ripples are distributed across different scales. Certain features in that spectrum appear unusually clean, as if the universe began with conditions that avoided wild irregularities. This cleanliness feels like the signature of a system that had its disorder drained away by a previous gravitational process. It is the cosmic equivalent of hearing an echo and realizing the original shout must have occurred in a very orderly room. Yet the most telling aspect of the cosmic background radiation may be something that is not there. There is no obvious imprint of an external universe, no directional signature, no temperature gradient, no scars betraying an outside influence. If our universe were born inside a black hole, it would not inherit visual clues about its cosmic parent. The event horizon acts like a perfect seal, preventing any outside features from leaking in. And that is exactly what we see. A background glow that is uniform, symmetric, and mysteriously self-contained. It behaves like radiation from a realm that was born alone, yet shaped by forces just beyond our view. In this way, the cosmic background radiation functions as a quiet archivist of our earliest moments. It does not give up its secrets easily, but it hums with the traces of an environment that was smoothed, compressed, and prepared long before galaxies ever thought about forming. If the universe did indeed spring from the interior of a black hole, the faint microwaves bathing the sky may be the closest thing we have to an ancestral memory. A glowing afternote from a cosmic transformation that took place behind a horizon we can never cross, yet somehow wrote itself into the fabric of everything we see. cosmic inflation is one of those ideas that sounds simple enough when you first hear it. An incredibly rapid stretching of space in the earliest fraction of a second. But the moment you try to picture it, your brain starts quietly backing away like it's been handed a physics textbook written in dolphin. Inflation proposes that the universe once expanded so fast and so enormously that the words extremely rapid feel like a polite understatement. It was not merely fast, it was space going full overachiever, ballooning from unimaginably tiny to astonishingly vast before ordinary expansion even got the chance to warm up. This sudden growth smoothed, flattened, and organized the early universe with all the enthusiasm of someone speed cleaning their house before unexpected guests arrive. The intriguing part is that this wild burst of expansion might not just be a convenient mechanism to fix early universe puzzles. It could be something far more fundamental, the natural behavior of a new space-time region forming inside a black hole. Inflation, in this view, is not an add-on to cosmic history. It is simply what happens when a newborn universe tries to take its first breath. To understand why, imagine what conditions would be like right after a black hole forms in a parent universe. The collapsing region becomes so tightly compacted that matter and energy are forced into an ultra-dense state. Inside, space-time is squeezed into something resembling a cosmic pressure cooker. If the interior geometry then branches off into its own domain, a new bubble of space-time separated from the outside by the event horizon, the newborn region begins its existence in an environment where densities and pressures are off the scale. In many portrayals, inflation requires a special field or exotic physics. But in the context of a universe budding off from a black hole, the required conditions might arise naturally. An infant universe that begins in such an intensely compressed state would be primed to expand explosively as soon as the constraints of the collapse are lifted. Inflation's defining feature, the way it stretches space uniformly, aligns beautifully with this scenario. When a new region of space-time is released from the crush of collapse, it does not unfurl slowly or hesitantly, it rebounds. Picture pressing your thumb deeply into a sponge. When you release it, the sponge does not return to shape timidly. It springs outward, restoring its volume swiftly. In the same way, a space-time region born inside a black hole could relax by expanding rapidly, smoothing out irregularities created during compression. This natural smoothing is one of inflation's most impressive accomplishments. It turns the newborn universe into a place where matter, radiation, and energy are spread evenly across vast distances. But instead of imagining this smoothness arriving as a miraculous coincidence, the black hole budding scenario treats it as inevitable. A region that begins small, dense, and uniform due to extreme gravitational compression will, when allowed to expand violently, maintain that uniformity on enormous scales. Inflation becomes not a special mechanism invoked to solve a list of cosmic headaches, but the expected behavior of a space-time pocket, rebounding from the pressure of a gravitational collapse. In fact, the rapidity of inflation matches the kind of explosive internal expansion one might expect if space-time were detaching from the parent universe's geometry. The moment this interior region becomes its own physical territory, free from the collapse that created it, it can grow in whatever direction space-time curvature allows. The equations suggest that this direction is outward, everywhere, simultaneously. That is inflation in a nutshell. Space growing faster than anything inside it can adjust to, stretching distances so fast that even light cannot keep up. A striking consequence of this interpretation is inflation's ability to erase prior structure. If our universe was born inside a black hole, the interior region initially inherits the compression of the collapse. But then inflation takes over and washes away the details of that inheritance. It stretches the region to such enormous proportions that any hints of its parent universe are diluted beyond recognition. This explains why the cosmos we observe appears self-contained and symmetric, with no directional imprints hinting at an external origin. Inflation wipes the slate clean, leaving behind a universe that appears to have sprung from nowhere, even though its deeper origin may lie hidden behind a horizon that no information can escape. Another alignment between inflation and the budding universe picture involves the uniformity of physical laws. In the earliest instance after inflation, the universe behaves consistently across vast scales. Gravity works the same way everywhere. Light follows the same rules. Matter builds itself from the same ingredients. This uniformity is astounding given how large the universe is. But if inflation occurred inside a space-time bubble that grew from a single tiny region, then every part of that bubble would inherit the same physical character from the start. It would all be governed by the same rules imprinted during its earliest compressed phase. One of the most evocative aspects of this interpretation is how naturally it frames cosmic inflation as part of a broader life cycle. Instead of imagining inflation as a mysterious burst that occurred for no particular reason, we can think of it as the natural opening act of a universe that started its journey in an extreme environment. When a parent universe forms a black hole, the interior geometry may pinch off and expand with breathtaking speed. The early expansion is not a random explosion. It is space-time settling into a stable configuration after being freed from the unbearable pressure of gravitational collapse. Inflation, seen through this lens, becomes a sign of cosmic inheritance. It is the moment when the new universe asserts its independence, stretching beyond its origins and unfolding in ways that no longer carry any trace of the collapse that birthed it. It grows so enormous, so quickly, that any memory of the parent universe becomes inaccessible, hidden forever beyond its expanding horizon. In this way, inflation is not just the universe's growth spurt, but the dramatic unveiling of a new cosmic realm, budding quietly from the interior of a black hole, then bursting outward into the vast, self-contained world we see today. If every universe is born from the interior of a black hole, then the cosmos is not a lonely only child, but part of a vast, branching family, an orchard of universes, each grown from the gravitational seeds of another. But here is where things get deliciously weird. There is no reason to expect every universe in this cosmic orchard to be identical. In fact, it is almost certain they are not. The physical constants, the deep settings of reality, the dials and knobs that control everything from how atoms behave to how galaxies form, might be slightly different in each offspring universe, and those tiny adjustments could mean the difference between a universe that forms stars and a universe that fizzles out before it can do anything interesting. Physical constants are the quiet custodians of the cosmos. They are not laws that tell you what must happen. They are the parameters that determine how it can happen. The strength of gravity, the charge of an electron, the speed at which light travels, the masses of fundamental particles. These numbers are startlingly precise. A slight tweak here or there, and the universe could behave in ways that defy anything we recognize. And if our universe was born from the interior of a black hole, then its constants might reflect the specific conditions surrounding its birth, much like a newborn inheriting some traits from a parent, but expressing them in its own unique way. Imagine the gravitational constant, the number that tells matter how enthusiastically it should pull on other matter. In our universe, gravity is actually quite shy. It is far weaker than the electromagnetic force, which is why your refrigerator magnet laughs in the face of the entire mass of the Earth. But what if another universe had gravity turned up a notch, just a little stronger? Stars in that universe might ignite faster or burn out quicker. Galaxies might form into tighter clusters. Maybe planets would be so firmly anchored in their orbits that even dramatic cosmic events could not easily disrupt them. On the flip side, if gravity were slightly weaker, stars might never reach the densities needed to fuse hydrogen, and the universe would remain cold, dark, and depressingly uneventful. Then there is the behavior of atoms. Atoms are ruled by constants like the fine structure constant, a mysterious number that controls how electrons interact with light and with each other. Change that value even slightly, and atoms might refuse to form stable structures. Chemistry, the very thing that lets stars burn, oceans swirl, and humans develop questionable life choices, might never get its moment. Some universes would be doomed to sterility, their matter too unruly to organize into anything more than diffuse clouds of particles drifting through meaningless space. Others might be too rigid, with atoms clinging so tightly that complex molecules never get the freedom they need to dance their biochemical dances. And we have not even talked about particle masses. Imagine a universe where electrons are heavier, or where quarks, those tiny inner building blocks of protons and neutrons, have different weightings. The periodic table might collapse into a single awkward element that does nothing except exist politely, or it might balloon with exotic elements that could form structures our universe is physically incapable of imagining. A universe with a different particle balance might have stars that glow in unfamiliar spectra, planets with materials unknown to our chemistry, or ecosystems built on molecular scaffolding we cannot even write down. If universes inherit their constants through the process of black hole formation, then each cosmic offspring might be shaped by its parent's personality. its mass, its rotation, its density profile during collapse. A rapidly spinning black hole might leave behind an interior region with different balance conditions from a quieter, non-spinning collapse. Those differences could imprint themselves on the structure of the budding spacetime, which then evolves its own constants as it expands. Each universe would be like an experiment performed by nature without supervision, each with its own recipe of forces and ingredients. Some universes might be hospitable to complexity. Others might be the cosmic equivalent of a freezer filled entirely with ice cubes, uniform, predictable, and utterly boring. This variation also introduces the tantalizing idea that universes might undergo a kind of natural selection, not in the biological sense, but in the cosmic sense. If universes that support the formation of black holes naturally give rise to new universes, then universes with constants that encourage black hole formation might produce more offspring. Over cosmic generations, this reproductive advantage would favor universes where the constants settle into values that allow stars massive enough to collapse into black holes. That does not mean universes are striving for reproduction, of course. Nature is not secretly running a cosmic parenting seminar, but the effect could be similar. Universes with certain constants would be more prolific, populating the multiverse with descendants that echo their successful traits. This does not imply that our universe is perfect, far from it. It just means it works. Its constants landed in the narrow window where matter can clump, stars can shine, chemistry can unfold, and black holes can form. But other universes could operate in entirely different modes. Perhaps in some universes, life forms emerge from exotic atomic structures stabilized by stronger electromagnetic interactions. Maybe in others, black holes never form at all, and those universes become cosmological dead ends. Or maybe there are universes where matter behaves so differently that the concept of life does not even apply. Realities shaped by rules that produce complexity beyond anything our imaginations can track. What this paints is a multiverse that is not just vast, but vibrantly diverse. Each universe is a separate reality, with its own internal physics tuned by the conditions of its cosmic birth. If each universe emerges from a black hole in a previous universe, then every black hole becomes a doorway to a realm defined by slightly different numbers, some familiar, some radically alien. Our universe's constants are not uniquely ordained, but simply the settings that happen to emerge inside the gravitational womb that birthed us. The multiverse, in this view, is not a monotonous archive of identical worlds. It is an explosion of possibilities, each universe a distinct experiment sealed behind its own horizon, each following its own natural laws like a melody played in a different key. Imagine the entire cosmos behaving like a grand evolutionary system, not with creatures battling for survival on planets, but with universes themselves shaping their futures through a quiet, cosmic version of natural selection. It sounds outrageous at first, the sort of idea you might scribble on a napkin at 4 a.m. after staring too long at the stars. But the more you sit with it, the more it starts to make an unsettling kind of sense. If each black hole can potentially spawn a new universe on the inside, then the universes that generate the most black holes would naturally produce the most descendants. And suddenly, the cosmic landscape begins to look less like a single, isolated universe and more like a vast genealogical tree where universes reproduce, mutate, and branch across an endless multiversal forest. The seed of this idea comes from a simple but staggering question. If universes can create more universes, what determines how many they create? The answer depends on how many black holes they contain. In a universe where stars form efficiently, grow massive, and eventually collapse into black holes, you would expect a healthy population of offspring universes. In a universe where matter never organizes into stars, or where stars burn too quietly to collapse, the black hole population would be small or non-existent, and so would the number of universe children. Without intending to, such a universe would almost be selecting itself out of the cosmic lineage. But this is not selection in the conscious sense. Universes are not sitting around adjusting their settings like cosmic engineers trying to optimize their reproductive output. Instead, it is natural selection in the most literal way. Random variation in physical constants produces universes with different behaviors, and the ones whose behaviors lead naturally to lots of black holes end up leaving behind more descendants. Over countless generations of universes budding off from one another, the multiverse could become dominated by universes whose constants are biased toward producing black holes efficiently. This is where the idea becomes both profound and satisfyingly simple. Our universe seems curiously well suited for the formation of black holes. Stars form in vast molecular clouds. Gravity clumps matter just enough to ignite fusion, but not so aggressively that everything collapses immediately. Nuclear processes inside stars create heavy elements, allowing some stars to grow massive enough to meet a dramatic end. And when those celestial giants finally collapse, black holes are born, quiet for a moment, then roaring to life as cosmic engines that curve space-time and swallow anything brave enough to venture too close. It is tempting to think of this as a coincidence, but in the natural selection picture, it could be the expected outcome of a long cosmic lineage. A universe that happens to have constants ideal for star formation and collapse would naturally produce more black holes. Those black holes would produce more universes. And those universes, inheriting slightly tweaked versions of their parents' constants, would be more likely to produce even more black holes. It is a feedback loop, not planned but emergent, shaping the multiverse over unimaginable cosmic generations. The analogy to biological evolution is surprisingly powerful. In biological evolution, organisms that produce more offspring are more likely to pass along their genes. Universes might behave similarly. The genes, in this case, are the physical constants and fundamental rules of each universe. If a universe's constants generate lots of massive stars and result in frequent black hole births, those constants get passed into more offspring universes, albeit with small random shifts. Universes that fail to produce black holes simply do not leave a legacy. They fade quietly, isolated realities whose influence stops at their own horizon. But what about mutation? If universes inherit their constants from their parent, but with slight changes, then each new universe might be a variation, a cosmic variant with its own quirks. Some changes would lead to fewer black holes, effectively reducing its ability to create offspring universes. Other changes might improve black hole production, allowing that branch of the multiverse family tree to flourish. Over time, the distribution of universes becomes heavily skewed toward those with black hole-friendly settings. This does not imply that universes intentionally optimize themselves. It simply means that the multiverse naturally amplifies whatever traits lead to more universes. This raises another mind-bending possibility that many universes in the multiverse may be radically different from ours. Our universe may be part of an especially successful lineage, with the right balance of forces for star formation and stellar collapse. But sprinkled throughout the multiverse, there might be countless universes where stars never form, or where gravity is too weak to make black holes, or where matter behaves so oddly that black holes cannot exist at all. Those universes are cosmic evolutionary dead ends, unable to propagate their traits into future generations. What this framework offers is a way to understand why our universe appears so finely tuned, not for life specifically, but for the production of complex structures that eventually collapse into black holes. The constants of nature seem suspiciously well balanced, and this idea suggests that such balance may have emerged through the quiet filtering process of cosmic reproduction.
The multiverse might be filled with universes that lean toward physical conditions that promote black hole formation simply because those are the universes that can reproduce. And here is where the picture becomes almost poetic. Each black hole is not just an abyss where matter disappears. It is a potential cradle, a cosmic womb, a passageway to a new universe that inherits the physical essence of the one that birthed it. In that sense, black holes become not endpoints, but beginnings, gateways through which the cosmos explores itself, generation after generation. This form of natural selection among universes paints a vast, interconnected cosmic family tree where no universe is truly alone. Instead, each universe is part of a lineage stretching backward into a past we can never observe and forward into realms that will never know we existed. It is a vision of reality where black holes are the seeds of creation, universes are the fruit, and the multiverse is the orchard, growing, changing, and blooming endlessly beyond the reach of our own cosmic horizon. Time is already one of the most slippery concepts the universe has ever handed us. We like to pretend it is a dependable river, flowing steadily from past to present to future. But physics keeps reminding us that time is more like a moody tide. It stretches, it slows, it bends, and occasionally it behaves like it forgot the rules entirely. In the context of black holes creating new universes, time becomes even stranger. So strange that the way time passes inside a black hole-born universe may bear almost no resemblance to how time passes in the parent universe outside. The very idea suggests that all our notions of before, after, during, and even now
may be deeply local phenomena, valid only within the boundaries of our own cosmic bubble. One of the first clues comes from the way time behaves near an event horizon. To an outside observer, anything falling toward a black hole appears to slow dramatically as it approaches the horizon, like a character in a movie caught in exaggerated slow motion. From the external viewpoint, the infalling object never truly crosses the horizon. It just fades and redshifts into darkness, frozen at the edge for what looks like an eternity. But from the viewpoint of the object itself, time flows normally. It crosses the horizon without hesitation, blissfully unaware that the outside universe thinks it is still hanging around at the doorstep. This mismatch in temporal experience hints at an important idea. Time is not universal. It depends on where you are and how space-time is curved around you. So if the interior of a black hole blossoms into a new universe, the time experienced inside that bubble could be completely out of sync with the time outside. The two regions are not just separated by distance, they are separated by the geometry of space-time itself. And that geometry controls how clocks tick. Picture a massive star collapsing in a parent universe. As it shrinks, the gravitational field strengthens dramatically. Time outside the forming black hole continues to tick on its usual schedule. But inside, at the moment the interior space-time begins to unfold into a new domain, that new domain may inherit no connection to the parent clock. Time inside could start fresh, like an entirely new timetable written on a blank page. This means the age of our universe, measured in billions of years from our perspective, may not correspond to any meaningful duration in the parent universe at all. From the outside, the entire lifespan of our universe might fit into a moment, or it might stretch across eons. The comparison may be as meaningless as comparing the temperature of a thought to the color of a melody, two realities governed by different rules. This disconnect grows even stranger when we consider the expansion inside a newborn universe. If the interior region expands rapidly, and inflation suggests it does, time inside stretches along with space. In this stretching, the pace at which events unfold can diverge dramatically from anything happening in the parent frame. What feels like billions of years inside might correspond to a blink outside. Or perhaps the parent universe has long since vanished, collapsed, or evolved into something entirely different, while time inside our universe marches forward at its own pace, oblivious to the parent's fate. The idea becomes even more intriguing when we consider causality. In ordinary life, cause comes before effect. You drop a cup, then it shatters. But at the boundary between a black hole and its interior universe, cause and effect become tangled. The event that triggers the interior expansion, the collapse of a star in the parent universe, may not line up neatly with the internal timeline of the universe that follows. Inside, the expansion unfolds in a sequence that feels natural and orderly. Outside, the collapse that caused it may appear frozen or infinitely slow, or even irrelevant by the time the interior universe grows large. This leads to a peculiar but important conclusion. Universes birthed from black holes are temporally isolated. they do not share a unified timeline with their parents. Each universe carries its own independent clock, ticking according to the geometry inside it. These clocks cannot be compared directly. They cannot be synchronized. They cannot even be meaningfully contrasted. The flow of time in one universe might be faster, slower, or just fundamentally different in structure from the flow of time in another. Time becomes a private property of each universe, not a shared currency. Now consider the reverse. What if a black hole in our universe is currently giving rise to a new universe inside? From the perspective of that interior universe, vast epochs may already have passed, with stars forming, galaxies swirling, and life perhaps evolving, all while only a few microseconds have elapsed here. Or perhaps we are too early in our own timeline, and no interior universe has grown large yet, even though it may someday burst into existence in a region we can never see. The two temporal landscapes, the one inside and the one outside, do not interfere or overlap. They are sealed, each a self-contained timeline. This isolation can be strangely comforting. It means time is not a fragile thread that must stretch across the multiverse. Instead, each universe carries its own version of temporal order, shaped by its geometry and evolution. Time becomes less of a universal truth and more of a local rule, a rhythm that emerges from the structure of each cosmos. And here lies one of the most profound implications of the black hole universe theory. Time began for us not because the parent universe reached some special moment, but because our internal space-time structure unfolded in a way that defined what time means within our domain. Time is not handed down from a parent cosmos. It emerges inside each universe, rooted in its own expansion, shaped by its own curvature, and experienced uniquely by its inhabitants. In that sense, our cosmic clock is not part of a grand cosmic schedule. It is the heartbeat of a universe that began its life behind an event horizon, ticking at a pace only we can experience, marking moments only we can perceive, unfolding a history that belongs exclusively to this cosmic pocket we call home. If there is one thing the black hole universe idea excels at, beyond melting brain circuits, it is its ability to rearrange our sense of cosmic importance. Humanity has experienced a long, dramatic history of being gently demoted by the universe. First, we learned that Earth is not the center of everything. Then we learned the sun is not special, just another star among billions. Eventually, we accepted that our galaxy is one of countless swirling spirals drifting in an ever-expanding cosmic ocean. But the notion that our entire universe might be just a single branch on a vast multiversal family tree, that pushes humility into a whole new register. It is the cosmic version of realizing your unique snowflake is actually part of a blizzard. This theory invites us to imagine that the universe we inhabit, complete with its galaxies, nebulae, superclusters, mysterious dark matter, and all the ingredients needed for life, is not the sole grand stage of existence. Instead, it is one of perhaps innumerable offshoots blossoming from black holes across an overarching multiverse. If each black hole seeds a new universe, then reality is not a singular entity, but a sprawling din of universes, branching endlessly like the roots of some impossibly ancient cosmic tree. And we are just one twig on one branch, perched at the end of an evolutionary limb that extends far beyond what we can ever observe. This idea can feel unsettling at first. We like to think of ourselves as living in the universe, a definite article with gravitas. But if our universe is one among many, the word "the" loses its authority. Instead of being residents of the universe, we become citizens of a universe. The shift is subtle linguistically, but seismic philosophically. It forces us to confront the possibility that existence is much, much bigger than the observable bubble of space and time we inhabit. We are not even a drop in the cosmic bucket, more like a droplet in an ocean of buckets. Yet, counterintuitively, this humbling idea can also be strangely comforting. If universes are continuously budding from black holes, then creation is not a rare, isolated event. It is happening everywhere, quietly, invisibly, constantly. The cosmos becomes not a static stage, but a living system, building new realms in a kind of ongoing cosmological artistry. Our existence becomes part of a much larger creative process.
We are not a lonely exception in a desert of nothingness, but one bloom in an infinite garden of universes. The grandeur remains, just spread across a landscape far more expansive than we ever imagined. One philosophical consequence of this view is a renewed sense of connectedness, not in a literal physical way, since universes cannot communicate across their horizons, but in an existential sense. We might be separated from other universes by impassable boundaries, yet we share a lineage. Just as every human carries genetic echoes of ancestors they will never meet, our universe may carry structural or physical echoes of the universe that birthed it. The constants we measure, the architecture of cosmic expansion, the very nature of matter itself, these may be subtle fingerprints left behind by a parent universe we can never observe.
And if our universe forms black holes of its own, then we in turn will pass along faint echoes to our cosmic descendants. It becomes a form of existence beyond existence, an ancestry written not in DNA, but in the curvature of space-time and the rhythms of physical law. Thinking of reality this way encourages us to rethink causality and origins. The old question, why is there something rather than nothing, shifts when creation is no longer a single moment, but a repeating process. Perhaps there was no moment when something suddenly appeared. Perhaps something has always been branching and budding, each universe sprouting from another in a chain that stretches past our ability to conceptualize. The multiverse becomes a timeless phenomenon, one where creation is not an anomaly, but a default state. This branching view also opens the philosophical door to a profound sense of scale. When we look at galaxies through telescopes, we see breathtaking expanses of space, majestic spirals, glowing clusters, filaments stretching like cosmic veins across billions of light years. But if universes themselves are numerous, then everything we see, no matter how vast, is localized. Our unimaginable size becomes modest compared to the infinite fractal of universes blooming from black hole after black hole. It is like realizing that the biggest ocean on Earth is still just a puddle compared to the oceans on thousands of unseen planets. Another philosophical thread emerges from how this theory reframes life itself. If the constants of a universe influence its ability to form stars, planets, chemistry, and eventually living organisms, then life becomes a byproduct of certain universal configurations that may only exist in universes tuned in a specific way. That means our existence is neither inevitable nor miraculous, but simply the result of being in a universe whose parameters fall within a narrow band of life-permitting options. The multiverse does not diminish life's wonder. It simply contextualizes it, placing life as part of a broader cosmic variation, like an unexpected harmony arising in one branch of an endless symphony. Perhaps the most profound consequence, though, is the shift in perspective it demands about knowledge and mystery. If our universe is just one branch among many, then the horizon of our knowable reality becomes a gentle boundary rather than a final frontier. Beyond it lies not emptiness but more reality, unreachable, unknowable, but not non-existent. Mystery becomes a built-in feature of the cosmos, not a temporary obstacle. It reminds us that the universe is not obligated to reveal everything. It can retain secrets, hide deeper structures, and operate beyond our capacity to observe. And that is part of its beauty. In the end, the idea that our universe is one branch on a vast, endlessly fracturing family tree does not make us insignificant. It does the opposite. It invites us to see ourselves as part of something unimaginably rich, a cosmic lineage, an unfolding tapestry of universes creating universes, a story far too large for any single cosmos to contain. We are not the main chapter. We are one wonderful sentence in an infinite, ongoing story that extends forever outward into the unknown. There is something undeniably irresistible about a theory that asks us to imagine universes sprouting from black holes like cosmic offspring, each one born in secret, nurtured by its own internal physics, and forever sealed from its parent by an unbreakable horizon. It is the kind of idea that sweeps your mind off its feet, not because it promises certainty, but because it opens a door to possibilities that feel both outrageous and strangely grounded. And that is the magic of this theory. It manages to stretch our imagination without drifting into pure fantasy. It dares us to think bigger while keeping one foot planted firmly in the realm of real, respectable physics. The beauty of this idea is not that it answers every cosmic riddle. It certainly does not. The universe still holds more mysteries than a library missing all its catalog cards. But this theory gives us a way to approach those mysteries with curiosity instead of intimidation. It tells us that not understanding everything is not a failure. It is an invitation to consider that our cosmic home may be part of a structure so vast and intricate that our current theories are only the first punctuation marks in a much longer sentence. One reason this theory matters is that it reframes what we consider normal. For most of human history, normal meant Earth sitting quietly at the center of everything. Then normal expanded to mean a solar system orbiting an unremarkable star. Later, normal became a galaxy filled with hundreds of billions of stars, all drifting through a universe brimming with even more galaxies. Now, perhaps normal will expand again, not to one universe, but to countless universes, endlessly budding from black holes, each with its own laws, its own stories, and its own possibilities. Normal is not a fixed point. It grows every time we dare to look beyond our comfort zone. This theory also matters because it reminds us that physics is not a dry set of rules, but a living, evolving conversation between our models and the universe's behavior. Every time we uncover a paradox, every time an equation spits out a surprising solution, the universe is nudging us to think more deeply. Black holes, for instance, began as bizarre mathematical curiosities, strange artifacts of Einstein's equations that seemed too ridiculous to be real. Now they are astrophysical celebrities, studied by telescopes, observed through gravitational waves, and photographed as glowing rings of light. If a once ridiculed concept like a black hole can turn out to be real, who is to say that a universe born inside one is beyond the cosmic pale? What makes this theory particularly engaging is that it neither throws away established physics nor insists that we settle for incomplete answers. Instead, it uses the tools we already trust: space-time curvature, gravitational collapse, general relativity, and combines them in new ways that reveal unexpected structures. It does not demand we believe in magic. It simply asks us to consider what might happen when physics pushes itself to extremes. And history shows that physics at its extremes often reveals realities far stranger than anything we invent in fiction. Another reason this idea resonates is that it reminds us of the universe's playful side. For all its seriousness, its equations, its laws, its relentless adherence to cause and effect, the cosmos also has a mischievous streak. It builds stars that explode in spectacular fashion. It shapes galaxies that swirl like cosmic pinwheels. It hides dark matter in plain sight. It sprinkles quantum uncertainty into everything as if to say, relax, not everything needs to make perfect sense all the time. A universe that spawns new universes through black holes feels perfectly in line with this playful complexity. It is extravagant, it is dramatic, it is almost poetic, and yet it is not mathematically forbidden. There is also a deeply human reason this theory matters. It gives us permission to wonder again. Modern science often emphasizes precision, measurement, and data, all of which are essential. But it is easy to forget that imagination is just as vital. The black hole universe idea rekindles the sense of awe that first drew humanity to the stars. It lets us imagine that our universe might be part of a grander structure, a cosmic family tree branching in directions we can never see. It makes us feel small, yes, but not insignificant. Small in the way a single note is small in a symphony, one part of a vast harmonious composition that stretches far beyond the reach of any one instrument. This theory also encourages humility in the best possible way. It tells us we do not have all the answers, and that is okay. It tells us that the universe might be under no obligation to match our expectations, that its architecture might be far more imaginative than our earliest scientific intuitions. It tells us that even if we could travel to the edge of the observable universe, we would still be nowhere near the end, because there is no end. Just more reality unfolding in ways we can barely fathom. Even if the black hole universe theory turns out not to describe reality, it serves a powerful purpose. It expands the territory of what we consider possible. It challenges us to examine our assumptions. It invites us to see the cosmos not as a simple machine, but as a dynamic, evolving, almost organic system with layers upon layers of hidden structure. In doing so, it strengthens the bridge between our imagination and the physical world, allowing us to explore big questions without abandoning scientific rigor. And perhaps, in the end, that is the real lesson this theory offers. The universe is stranger, richer, and more playful than we ever expected, not because it must be, but because it can be. Reality is under no obligation to be small, tidy, or easily explained. It is free to grow, to branch, to fold itself into endless patterns. Our job is not to shrink those possibilities, but to follow them wherever they lead with curiosity, humility, and a sense of wonder worthy of a cosmos that may be forever exploding with new worlds hidden within its darkest corners.